Hello, everyone. This is the webinar on AI and unlocking innovation in advanced materials. Straight over to Patrick Maestro, the Secretary General of Eurocase, for the welcome. Patrick.
Looks like, can you hear me? Yes. So very happy to see you all. I'm the General Secretary of Eurocase. Eurocase is the network of the engineering academies in Europe, 23 academies gathered in Eurocase, more than access to more than 6,000 experts in all areas of engineering and technology. And you can see our website if you want more info. We have to go directly to the presentations now. We have been involved in this advanced material report, of which you will hear today. I just want to thank all the participants to the report. It has been an extraordinarily big amount of work, and with a special thank to Anke and Oli, our chairs, and all the working group. With this, back to you, Louise, for to get into the real thing.
Thank you, Patrick. As Patrick has said, we're looking today at two pieces of work that came out in April. They're at the website that you can see on the right-hand side. One is an evidence review report and the other is a scientific opinion. The format of today's webinar is going to be as follows. We've got the opening and welcome where we are now. We will then have some background and context to the two pieces of work we've just shown to you. There will be about half an hour of presentations by members of the panel, followed by discussion and Q&A for around 20 minutes. And we will finish on the hour promptly with a wrap up and close. The chat is open, which you are very welcome to use, but we also encourage you to pose questions to members of the panel. But to do so, please use the Q&A box. We're not monitoring the chat box for questions, only the Q&A box, so please use that. The speakers that we have today, four eminent speakers. The first, Anke Weidenkauf, who is a professor of sustainable materials science at Darmstadt in Germany, and was a co-chair of the SAPEA working group on advanced materials. She's followed by Dimitra Simeonidou, who's a member of the group of chief scientific advisors and a professor at the University of Bristol in the UK. She's followed by Nicola Mazzari, who is a full professor at EPFL in Switzerland and also the Cavendish Professor at the University of Cambridge, and was a member of the SAPEA working group on advanced materials. And then finally, Carsten Reuter, who is a director of the theory department at the Fritz Haber Institute at the Max Planck Society. It's important to note that all of the speakers speak in an individual capacity, and those opinions may or may not reflect the policy or opinions of the EU or the European Commission. So handing over now to Geoffrey Delamere, who works for the European Commission at the SAM Secretariat, who will give us some background and context. Geoffrey.
Yeah, good afternoon, everyone. So just a a few words about the Scientific Advice Mechanism, or SAM in short. It is composed of three parts. So there is a SAM Secretariat, which I am part of, which belongs to the European Commission in the Directorate General for Research and Innovation. And then there is a group of chief scientific advisors, which is represented today by Dimitra Simeonidou, who is a group of 7 experts appointed by the commissioner and who wrote the scientific recommendation. And last, there is SAPEA, which is a consortium of academy networks, which can reach out to more than 100 academies across Europe, and that can form working groups, organize workshops to support gathering of scientific evidence, And it's very important to know that they work independently from the rest of the process. So they are their own peer-reviewed documents that is written independently from the Commission and from the group of chief scientific advisors. So all three parts of the SAM are independent. And in a way, the SAM works at the interface between the scientific community and the European Commission. So the role of the SAM is to translate scientific evidence to inform policymaking at the European level. And what it's also important to know is that the SAM informs directly the College of Commissioners. So it's really a high-level tool, and the scientific reports that are produced are directly handed over to the College of Commissioners. So about the advisors, as I said, it's a group of 7 experts, which is represented today by Dimitra. They cover very wide scientific expertise and also geographical expertise, and they are appointed by the Commissioner for Research and Innovation, Ekaterina Zahareva. And the work, or like the SAM is coordinated by the SAM Secretariat, which is a small team which I'm part of at the European Commission. So we act as a liaison between the SAM and the rest of the Commission. We coordinate the scoping paper to really make sure that the colleagues, the policy officers requesting the scientific opinion we coordinate with them the scientific question that they want to ask, and we make sure that this question is scientifically relevant. Then we also support the advisors with the administrative and record keeping. We work with SAPEA to coordinate the work of the working group. And last but not least, we analyze the policy landscape. And this is very important to have a comprehensive overview of the policy landscape at the European level, but also at international level, to make sure that the scientific recommendations produced by the advisors really fit into the right policy landscape. And finally, there is SAPEA. It's a consortium of academy networks, and they can reach out to 120 academies across Europe in all scientific disciplines. They provide independent scientific advice, as I said before, so they are really independent from the rest of the process, and they inform the advisors by issuing policy options. So how we work, we first receive a request from the European Commission. So as I said, we liaise with policy officers to develop this scoping paper, which is then validated by the Commissioner for Research and Innovation. So in that case, it was Katarina Zahareva. Then we review the evidence, and this is where SAPEA works. So they set up a working group, and they produce an evidence review report. Then using this evidence review report and by putting it in perspective with the policy landscape, the advisors will write the opinion. And finally, we deliver the advice again at high level. So we have a handover with the commissioner or one of the commissioner in charge of the requests usually. And in the case of advanced materials, so we received requests in April 2025 by a commissioner in charge of startup research and innovation, Katarina Zahareva. And the 2 questions were the following. What contribution can advanced materials bring to the EU strategic autonomy? And also, how can the cross-fertilization of innovation in advanced materials be enhanced? And it's important to note that the commissioner wanted AI and digitalization to be a crucial part and to be something to consider by answering these 2 questions. And this opinion that was handed over earlier this year will inform the Advanced Materials Act, which is due by the end of this year. And I think that's my last slide. So thanks a lot for attending, and I hand it over to you, Louise.
It is. Thank you very much indeed. On to our first panel member, Anka, who's going to present the evidence review report. Anka, over to you.
Hey, hello, my name is Anke Weidenkaff. I'm the co-chair of this Advanced Materials Group, and I will tell you a little bit about our evidence report. So our topics were, on the one hand side, the sustainability, the concepts, processes, and best practices. We have in chapter 3 the emerging technologies and manufacturing, and infrastructure. And the chapter 4 was on basic research, which is very important for future transitions. And then we dedicated a full chapter 5 on the digitalization, simulation, and AI. And Nicola will report on this a little bit more detail. And of course, 2 chapters are on the policy options for European leadership, as already discussed by Geoffrey. Next slide, please. So the key messages are the following. We concluded that advanced materials will play important or the role in all sectors of new emerging technologies. So always you have first the materials and then the emerging material technologies. And here the sustainability will be very crucial in the future. And we have to develop circular strategies so that we can reduce the raw materials dependence and also in the future avoid the deposition of waste in the environment. And we also concluded that fundamental science is most important and requires long-term predictable funding, and we should not have expectations on rapid return, but without fundamental research, there will not be any technology. And then, as said already, and what is a discussion topic of today, the digitalization, AI, and machine learning technologies, they can have a very big impact on how material properties are being developed in the future if we are using them as a tool. And then as conclusions, we have to deal with the fragmentation of the ecosystem and the regulatory frameworks in Europe. And there is a big need for skills and resources to speed up the AI innovation needs or to address those needs. And we require a coordination mechanism in this European innovation ecosystem. Next slide, please. So the key messages for chapter 5 are that we have a data-driven approach and AI, which is becoming a central approach to advanced materials design. We need high-quality databases built on fair principles, and this improved data mining and curation are needed to strengthen reliable data pipelines. And we think that AI can enable next generation digital twins and self-driving labs to scale advanced materials discovery. Next slide, please. So also the artificial intelligence is a driver of sustainable materials and circularity. So if we have a good data set, then we can imagine digital twin, which is helping on recycling procedures. So if we have then a well-informed and smart waste bin, then this waste bin can deliver the components and the content of this waste to the research and production facilities, and this will then enable an AI accelerated sustainability. Next slide, please. And this is a slide I received from one of my colleagues, Hongbin Zhang, who was making me very happy, because also here you see that the data-driven discovery is also becoming a little bit more circular, not so linear as in the past. So in the past, on the left-hand side, you see that we were always using hypotheses to have a data-informed and then data-driven materials research and development. So in the future, that's his vision, is that we will have also a more circular approach, so that we are using then this data-driven materials research. We have the AI augmentation, and then maybe we can even have an AI native circular development, which can enhance the discovery of new materials. And that's what we will discuss today. And I'm handing over to my colleague. Thank you very much.
Thank you very much, Anke. We move on now to Dimitra Simeonidou. Dimitra.
Yes, thank you. And a lot of background has been said. I represent the group of chief scientific advisors as part of scientific advice mechanism. And what we have produced during the last year is based on the SAPIA scientific evidence review and also the policy background. Our job is to take those into consideration and produce a scientific opinion which actually informs, hopefully, policy in this particular field. So this scientific advice, the scientific opinion together with the evidence review, they were presented on the 21st of April, so 1 year exactly after the request to Commissioner Zakharieva. And you see here my colleagues from SAPIA and from GCSA presenting to the commissioner. If we go to the next slide, please. So what has been at the focus, I suppose, both for SAPIA and for ourselves, is looking at advanced materials, how we can achieve strategic independence for Europe, how we can increase industrial competitiveness and growth, and how we can do this by keeping actually safety for EU citizens and sustainability in mind. And as it was actually mentioned before, in order to do that for a sector as wide and as complex as advanced materials, we have to realize what the challenges are, and they are diverse, wide, and not homogeneous challenges across the different advanced material domains. But there are definitely challenges around knowledge, around metrics on how, for instance, we measure success, and on data. And data is a big area that we are discussing today because they feed and they're the fuel for AI. We realize that one of the challenges is value conflicts across discovery, scientific discovery, for instance, and commercialization, and other issues around complex governance. Anke also mentioned fragmentation, and fragmentation is a big issue, and that is around infrastructure, skills, and funding. And this fragmentation is both in terms of geography, but also in terms of advanced material sector. What is important for today's discussion is this, what we see as different data formats, different data presentation, data languages, and also limited interoperability in some groups of advanced materials more than the others. And of course, we have systemic challenges and geopolitical constraints, and I'm not going to go into more detail about this. If we go to the next slide, I mentioned that safety and sustainability is very much at the heart of what we have been thinking. There are strong European values, but also they're being criticized a lot of times as being actually barriers to innovation and speed of commercialization. So we put a structure in our opinion where we actually say, yes, we have to be safe and sustainable by design, but not overburdening growth. And therefore, we actually looked at the interventions and different technology readiness level. So for instance, when you are at the discovery phase, then of course, hazards and safety is there, but has to be anticipated, not addressed fully. And the same when we are looking at circularity, we would like something to be circular by design, but it's part of the discovery process rather than actually having the full, creating the whole ecosystem and the discovery side. And of course, when we are going to the higher TRFs, then we start looking about anticipating regulation, creating the right data formats, and doing proper assessment along circularity, but actually the full regulatory and legal frameworks, and also creating a circular ecosystem, it comes when we are market ready. So in TRL 7, 8, and 9, then all these considerations that they have been anticipated, they come together and into effect. And if we go to the next slide, across the whole process, and generally when we are doing science these days, AI and digitization is very important. So when we looked at advanced material based also on the evidence report, we have a specific recommendation, which is to support the creation of fair data spaces to actually enable digitization, AI, and computational methods across the whole chain of advanced material from the conception design all the way to commercial propositions. So there are 5 parts in this recommendation. The one is looking actually at data and how we can create that pipeline of fair plus data and AI ready data across Europe. And we know that there are challenges on that. The plus here is going beyond fair because we would like our data to include also safety and sustainability information as much as possible. So we are talking about using AI to connect data spaces, to back the development of common data languages, but also to unlock existing scientific literature for AI. In the second part, we are looking actually how we can boost modeling and experimentation for advanced material research and development. And if I go, modeling is a strength in Europe, but if I go into experimentation, how we can make experimentation open and as a utility for the European ecosystem, looking, for instance, access from academics and SMEs as well as large companies if necessary. So that comes the recommendation about self-driving labs and digital twins as an enablers and also as a utility use. And then the 5th part of this recommendation is how we can promote digitization and AI, not only on the advanced material creation and production, but also in the whole chain, including also commercial models, including considerations for safety and security. So this is our recommendation. And if we go to the next slide, you can read all of this, of course, in the documents, including the scientific opinion. It's much more of what I describe here. So if you go to the SAM website, you can find all this, including the video of the handover to the commissioner. Thank you very much.
Thank you very much indeed, Dimitra. And now we move to our third speaker, who is Nicola Mazzari. Nicola, over to you.
Thank you, Luis. And I guess to make it absolutely clear, I'll start with the take-home messages. One is broad and is the entire response to the request from the EU. But it's always good to remind why materials are important. And I often repeat that they are the enabler of the technology that drive our economy and sustain our society. So if you think at electrification and how we can drive an electric car, or we can have a all-day charge on a laptop or a phone, is because of lithium-ion batteries, invented in the mid-70s, commercialized in the mid-90s. If you ask yourself why electricity becomes almost free in Spain at noon, is because we have advanced manufacturing of solar cells that are able to turn solar illumination into electricity. So that's the first take-home message. And the next one, and that was really at the core of this chapter that I prepared with Luca Ghiringhelli of KIT on simulation data and AI, is that we are really going digital, and digital at many levels. So we are going digital because we can do quantum mechanical simulations of materials on the computer. We go digital because we have a lot of data that can be used to train our machine learning models, and more our artificial intelligence generative model. And this paradigm shift is changing the way we do scientific discovery and technological innovation. In fact, we have seen it coming. In the next slide, there is an interview I gave to Baron that identified, 7 years ago, what would be the $1 trillion technologies. And, one was artificial intelligence, one was Cas9 genetic editing, and the last one was advanced materials. And this materials revolution coming from the combination of simulation, data, machine learning, and AI. So what we do with all these capabilities, in the next slide, I summarized maybe for the expert, what people like me and Carsten often do day to day. That is, we use simulations to understand, predict, but especially design and discover novel molecules, novel materials, novel processes. We often work very closely with our experimental colleagues, and as Carsten will show, we actually now have new experimental colleagues that are a bit less human. And because we are all relying on a digital paradigm, we really proceed at the speed of information and communication technologies. Every 18 months, our capabilities becomes twice as fast. As I highlight in this slide, I was giving a talk one evening. In the next slide, to, I would say, 40 billionaires, and they were all falling asleep. And so I told them that the business model of what we do is 100% returns every 16 to 18 months. And this just means that, the computational capabilities upon we base what we do actually follow the speed of computers. And the impact of this is very wide. In the next slide, I'm using a recent publication on Nature that asked itself, what is the most cited field in science, medicine, engineering. And you might think DNA, or you might think cancer, but actually they did that in 2014 and did it again in 2025. It's really quantum mechanical simulation. Who could believe it? The most represented field. There are 12 papers in the top 100 most cited ever, and 3 in the top 10. And now this is not only academia. If you go to the next slide, I mean, what has been remarkable is that in the past 3 years, I would say, major companies have gone massively into materials discovery. From Microsoft, these are Nature papers on, generative artificial intelligence, inventing new materials, to Google DeepMind. You probably all know DeepMind from AlphaFold and protein folding. Now materials is the next challenge for them, or Meta, Facebook, that produces some of the most used models in academia to understand the materials properties. And these are the big companies, but again, in the next slide, these are just a few core startups that in the last 18 months very quickly garnered just $1 billion in, say, first round funding. And so let me conclude, where is Europe in all of this? It's in a wonderful position. Actually, the world run on European codes, and, we should capitalize on that. I mean, in particular, the two most used codes for material simulations, quantum mechanical, are VASP, which is a commercial code out of TUVN, and that Quantum Espresso out of CISA, but many others. FHA Ames is one coming out of Fritz Haber and Berlin. And it's not only in Europe. This is really, a world-leading capability, historically in simulations, but now also in data. Alexandria, the largest database of curated inorganic materials. Nomad, also in Berlin, Materials Cloud, and so on. And so let me conclude with the last slide. Where is AI in all of this? We have the capabilities to simulate. We have the capabilities to deploy machine learning model that learn from the simulation, learn from the data, and really allow us to get to the answer much faster. But now we have really the large language models as knowledge integrators and the artificial intelligence agents as driver of simulation. So you can now ask, and this is just the last click at the next slide, you can just ask a question in natural language. And when I was a student, took 6 months of training to be able to deliver. Now an orchestrator, in honor of Carsten, I call it the von Karajan, the orchestra director, is able actually to do everything that a human could do. And so we're really changing, I would say, the paradigm of how we do science. Thank you, Louise, and thank you all.
Thank you, Nicola. That was excellent. And to our final speaker, Carsten Reuter at the Max Planck. Carsten, over to you.
Well, thank you, Louise. And I think you can directly click to the next slide, please. So one thing that one should highlight in everything that Nicola has said is that these increased capabilities that we have are not just solely due to increased computational power that we have or advancements in the individual methodologies that we're using, but in the entire way how we are actually working. So when Nicola and I were young and powerful young PhD students 30 years ago, the way how we would work would typically be that we manually write input files for the different software packages that we were using. We would send this off to a queue to be computed in a high performance computing center. We would wait for a while, and eventually the results would come back, and we would analyze them manually with a lot of training that we needed in order to actually understand this kind of data. We have completely changed this. We are now using very complex workflows. There are even workflow managers that allow us to actually handle very, very complicated workflows that work autonomously, and also with an AI increasingly taking over, as Nicola has shown on his last slide, to actually devise the plan of how we should actually do these kind of calculations. And up to now, most of this has actually been done with calculated data, as Nicola has pointed out, so quantum mechanically generated data. This is naturally that it started there because this is easier to create. It's already in the computer. But many application areas in material sciences where the sim to real gap is still too large, where you cannot approach stuff yet with simulated data. And then the natural thought is, can I not sort of like do it with experimental data and instead still use all of this knowledge that I have of automated workflows with experimental data? And next slide, please. This then has given rise to what is now called self-driving laboratories or materials acceleration platforms, where basically you have a confluence of AI and automation and robotics in the laboratories. On a timeline, originally both the individual experiments, so the creation and the analysis of the data, was manual and very, very slow. In about the 1990s, there was a lot of effort on automation of experiments, developing high throughput kind of platforms. In chemistry, this was called combinatorial chemistry. Around 2010, we entered the big data era, where then sort of like analysis of the data was accelerated. And now basically these maps or SDLs are putting all of these pieces together, and you have autonomously operating labs where the AI controls the individual experiments and does also the planning of the individual experiments. The movie shows a lab that we're currently building up in Berlin, together with Siemens Energy and BASF, for example, where we put the catalysts as thin films on wafers so that we can simultaneously study entire gradients of catalysts. Next slide, please. The individual tasks that are needed to be done is, as I said, experiment planning and control. So the planning really sets up the AI, tells us what kind of experiments we should actually do next, which really give the best information that we have at the current stage, or would give us the next new information so that we can refine the models. In order to do so, we need to also control the individual experiments. We need to digitalize them and have them run autonomously. This is very important in materials research because we have very complex analysis methods like electron microscopies or spectroscopies, and we don't want to have humans anymore to operate them. Big examples, for example, being that the data streams are still so large that humans cannot really digest them on the fly anymore, or that the experiments run so long that also a human cannot operate on this all the time anymore. This is becoming, of course, increasingly important because of sustainability. We need longevity tests, experiments that run for weeks and months, and no human can operate them. And instead, we have agentic systems that run these experiments for us and analyze them on the fly. And just as a very quick final slide, just to show you that this is not all science fiction, but actually already reality. An example from our own work, we built up a self-driving lab together with BASF to find improved catalysts, and we had an automated synthesis. Next slide, or click, please. So that basically the synthesis of new catalyst materials was fully automated. Next click, please. Then they were automated, tested in a parallel reactor, and this kind of information in an active learning loop. Next click, please. was fed into an AI model, and it really only needed us less than 100 experiments to search a space of about 10 to the 12 different catalysts that in principle were possible to find something that is better than the catalyst that BASF is currently selling for this kind of reaction. And so you really get a dramatic speed up from years, decades to weeks. And with that, thank you very much, and back to you, Louise.
Thank you, members of the panel. You've left plenty of time for Q&A, and for that, we're handing over to Patrick, who's going to lead the Q&A. Patrick.
Thanks, Louise, and thanks to all the speakers for exactly being very concise in the presentation while giving a lot of details. So the Q&A session is open, and I think we have 2 or 3 questions already. We have 2 questions from the last meeting, which I will take first. And so I think I have to read the questions. I will take the second one, and because I think, Nicola, you addressed partially the point. Europe is traditionally has not been tremendously innovative, but rather perfecting innovation. In your opinion, how is this scheme can have a change in the world of AI? That means, are we different within AI? Nicola, I think you discussed that in your presentation.
I'm happy to start very briefly. I actually think that we are very innovative. Sometimes what we are slower is turning innovation into technology. The entire process of startup, small company, large company. But AI is what I call a disruptive technology, so it's a bit of a level playground for everyone, and almost everyone plays on the same level field.
Any other comment from the panelists? Carsten.
I would tend to agree. I would have really seen the situation really on the opposite. So Europe has always been very innovative on the fundamental level, and we had troubles with translation and really making it into a technology. And I think the acceleration that AI is opening up, but also one has to admit that the hype that is currently created around it brings in much more attention and much more money, and you suddenly see many more startups in our area. Nicola has pointed to quite a number of them with simulated data. There are equally as many startups, for example, that now work with self-driving laboratories, huge amounts of money. And this is all very much centered also in Europe. So I think we are entering a good period now, because this translational problem that we had in the past could actually be mitigated.
Thank you, Carsten. And I think that what you showed us, the implication of big groups like BASF and you, is also a very good sign, because, of course, this is important to see the big groups involved in that and taking these kind of risks. Any other comment on this question? I don't see all the panelists in my screen, so don't hesitate to speak, Dimitra or Anke. I think it's okay. The second question of last time was the use of AI tools and models for modeling of advanced materials have been touched upon. How is data governance and data sovereignty handled, considering the AI Act excludes research, as far as the person who asked the question understood it? Who wants to answer? Maybe that's for you, Dimitra.
Yes, happy to start on this. So we discussed this topic across the GCSA quite widely. And of course, as a scientist, not a material scientist, but a scientist nevertheless, when we are looking at the discovery side, the low TRLs, we would like to see as much as possible open data, and open data that actually they are providing from research into the community, so they can further use them to innovate, and to innovate not on the AI space, but more than that, on actually creating, reuse, expand, and so on. So one of our recommendations has been that when we see academic research or institutional research funded by public monies, to make a requirement and rewards associated with opening data and make this data available, and that address that fragmentation question as well, considering that the data are reusable, traceable, and trusted, and that is a very big question, how you can make this data actually traceable and trusted. And then what we went, we also realized the realities of making data open. So we have actually suggested, in our opinion, a tier system where actually we can move of completely open, low TRL academic research in terms of data into different tiers where there are certain service level agreements set in terms of who is accessing the data and how the data are being accessed. Our recommendation there is for the European ecosystem, we try to keep the access open and fair as much as possible, but taking into account geopolitics, taking into account, for instance, considerations around national security. And we eventually reach sets of data that they are actually exclusively accessed by certain actors. I mean, that reflects reality. And of course, it is up to the community within the discussions and implementation of Advanced Material Act to implement a recommendation like this and give more clarity who is going to be access what data and how, and within that tiering system, how actually we set the boundaries of those tiers. But governing, opening, using data for innovation is a very big topic, and actually is the most fundamental challenge that we are having to create that capability within Europe.
Thank you, Dimitra. Any further comments on Dimitra's answer?
A super brief one, in the sense that, it's been an interesting challenge, even between industrial partners, on how to have them work together when they actually, don't want to share the data. And there is a lot of interesting science, but practical relevance on actually, training models on data and sharing the models rather than having to share the data and somehow open, sort of bypassing some of these constraints about the fact that data belong to these confidential peers.
Thank you. We go to the next question. Is a bit related. How can we safeguard against AI hallucination and the black box, into brackets, blind spot in materials modeling and characterization? And does open science play a greater role in improving European resilience and competitiveness in AI-driven materials innovation? Who wants to take this one? Carsten.
So there's a short and a longer comment I can make on this. The short one is, how can you prevent any AI from hallucination? Well, more data. Very simple. Of course, you need to provide the relevant kind of data, and that is also a key question, how to generate this. The little bit of a longer story, which is actually quite interesting, is that within also the AI circus, understanding suddenly receives sort of like experiences a renaissance. Much of the early AI work that we have seen in our field, if you want to call it badly, you could call it a black box optimization. That's very often what has been done, because that sort of like is the simplest first things that you can do. And black box optimization has or misses something that is very, very critical that we humans have, and that is called open-endedness. So we never finish a task. Whenever we're close to finishing a task, the understanding that we have generated already leads us immediately to hypothesis and to coming up with the next tasks. And you want to implement this also into AI. And open-endedness necessarily builds on understanding. And so now also you see a lot of work also from the language models, etc., that includes reasoning. So you want understanding. And because that is sort of like the leverage that you have to create sort of like the next ideas and the next hypothesis. And understanding is a killer of hallucinations because we as humans can understand that and can see whether we agree with the reasoning. And then sort of like we see if hallucinations happen. So I think overall, yeah, a big problem, more data saves, but also the way how we set up our AI in creating understanding, also for us humans to control it and to be able to understand what it does, but also for open-endedness. This will be a key to abate hallucination in the future.
Thanks, Carsten. Dimitra.
Yes, I agree with everything said 100%. Just to add very, very briefly that models hallucinate less and less because of the availability of data. So we are not at the same point that we were 2-3 years ago. Second, in terms of, as an addition to reasoning, explainability is a very big, actually gives a big complementarity in terms of actually dealing with hallucinations, so explainable models. And I would like to mention open sourcing models, because actually an open source environment is giving that opportunity to co-create, co-develop, and therefore advance model fidelity through open source practices. And this is, I'm not sure how much this is a practice in advanced materials, but in my own sector, for instance, open source is a key practice now exactly to address hallucinations, trust, fidelity, stability, and all these key worries.
Thank you. I will take another question related. Well, we're dealing with open data and open software. The question is, we love to publish open data and open software, but if I want to create a startup, I need to protect them. Otherwise, it's hard to convince investors that our product is unique and competitors won't exploit it. Which strategy do you recommend? Who wants to take it?
Well,
It's
maybe
a difficult question, Nicola.
I can do a quick try. I think one has to have the App Store model. That is, there are capabilities that are open and very powerful. The simulation codes, the data, and you probably want to leverage those because they are high state of the art and available. And the product, the technology that the startup you develop is something unique that leverage all that there is, but really responds, we can call it to a market need or to a technological need that, this, broad, if you want, infrastructures cannot yet fulfill.
Having been in industry and supporting startups, I would completely agree with you, Nicola. Any other comments on this one? No. So there was, if I take back to the list, there was a direct question to you, Nicola, again. I have always one big concern that AI models are often trained on DFT data, but DFT itself, I'm sorry, itself contains systematic errors because of the different functionals, PPs and numerical settings. How can we prevent AI from learning these biases and becoming confidently wrong outside its training domain?
Yeah. So I think there are two elements. So one that we call verification, that is making sure that we provide the numerically correct answer. When you mention pseudopotential numerical setting is about that. And I think automation has made it possible, this. And there was last year a major effort from 40 groups verifying pseudopotential versus all electron calculation. So I think we are already, I think, in the world of numerical accuracy. What is missing is indeed the physical accuracy. DFT is a great theory that is exact in principle, but is approximate in practice. No one knows the exact functional. And if we were smarter, we would, call it the God's functional, like the particle physicists call the God's particle, and then we would receive billions to fulfill it. So I would say, half of the materials world is very much reachable by the current capabilities, and the other half is where indeed we push the academic research, we push the capabilities, the beyond the DFT techniques.
Thanks, Nicolas. Karsten, you want to comment?
I think exactly these kind of systematic limitations of DFT as a primary source at the moment, one has to admit, of material simulation, is one of the motivations for the experimental thread that I described in the self-driving laboratories, because at the moment we sort of I think portrayed it in a sense as separated. So Nicola describing the quantum mechanics calculation part and I'm doing the experiment. In the future, in these complex workflows of these labs, you will have both simulated and experimental data coming together, and they can check on each other. So the simulated data have systematic problems, systematic inaccuracies, but we have the numerics under control. That's the homework that we already did in this community in the last 20 years. On the experimental side, you don't, of course, have any systematic errors in principle because it's experimental data, unless you have some fault in your setup. But at the moment, we are having big problems in many areas with interlab reproducibility. There are so many hidden parameters yet that we don't understand yet as humans, and we cannot control that. So data that comes from different labs in principle should be the same, but it isn't. But so I think the two types of data sources complement each other. And in future, more complex workflows, they can sort of also then be used to check on each other. In some respects. It's not that this is already worked out and I can tell you a clear plan, but obviously conceptually, this is the next step that will come, and that should be sort of bringing us a big step forward. Also, for example, in towards developing the God's functional, when we have experimental data in large scale, and then we sort of can benchmark whatever functionals we develop against this.
Totally agree with you, Karsten. Next question is: are there any estimation across the board as to how much digitalization, AI, and autonomous labs, digital twins, can speed up the current 10 to 20-year advanced materials development timeline from research to market? The TRL 7 plus.
Yeah. Yeah, maybe this is also something we are thinking a lot about, how the processing of samples is being better described and read out from the papers. So as Carsten already said, this is still a challenge for the future, because I think Nicola showed this a little bit, that the companies are now very proud of having 2 million new structures. I think this is, for me as a solid state chemist, not so impressive, because there are 300 million compounds, and if you understand defect structures and the influence of the synthesis on the materials, then there will be much more. Then 2 million is nothing. And I think that this is really the great challenge, how to bring in the chemistry background and the knowledge of the preparation methods into this new world of self-sustaining circuits. I think this is still one big research question we have ahead of us, and I think this is very interesting and challenging also to use our real data and how to combine and benchmark them with the training data.
Thank you, Anke. I'll try to get all the questions answered. It's not easy because we're many, and thanks to the attendees. How do you see AI facilitating the design of material synthesis, given the diversity of synthesis methods and routes available? And in your view, what is the biggest hurdle to wider adoption today? Maybe even for you, Karsten, as you mentioned, you showed us some synthesis of material on thin films, but not only, and catalysts.
I can try. I mean, obviously, this should be my thing, but I have to directly tell you a disclaimer. I'm a theoretical physicist who now ends up doing experiments in chemistry. So, careful with what I'm saying. I think this is indeed so like a very, very important and critical area, because if one is fair and honest, everything that has been automated up to now is basically liquid handling. So most of the progress that we see is basically pouring A into B, moving stuff from somewhere and then holding something into a liquid. That's relatively easy to automate. You can still already synthesize quite a lot of things with these sorts of things, but they're really complicated inorganic synthesis methods, and Anke knows much more about this than I do. They are much more difficult to automate and to probe. And this is, I think, one of the next challenges that we have, that we really address automated synthesis for inorganics. But the advantage that AI will bring there is that we can lift this to a much more systematic level, because there's so many possibilities of how you can do. To what temperature do you heat for? How long do you keep it at which temperature in the autoclave? How do you mix things together? How do you do a ball milling and granularity? All these sorts of things. And up to now, this has been done by humans, by curiosity, serendipity, somehow playing a little bit around. In principle, you're navigating I don't know, X-dimensional space of possibilities, and an AI admittedly can do that much better than we humans. And I think if we now have the experiments automated and then unleash the AI algorithm on it, I think we will see huge advances in synthesis capabilities.
Thank you. There was another question related to Nicola and Carsten. How would you characterize the output of these AI-driven systems in terms of novelty? Do you see any potential limitation in the capacity of these AI systems in generating something truly novel?
I would say that, but that's just my opinion. Right now, I really see them as very efficient executors. Okay, they might not have the perfection of an ideal human being, but human beings are also imperfect and they make their own set of errors. So to me, right now, there is an empowerment of asking questions in more general terms without having to worry about how long does it take. I'm not going to ask a question to a student that will take 2 years to answer and might be useless, but I can use it. So I see them as accelerators. I don't find AI still, very innovative. It gives very competent answers to interesting questions, but it frees up my time to ask the interesting questions.
Carsten, addition?
Yeah, I agree with Nicola. I mean, quite frankly, at the moment, we humans still draft the design spaces. So we say this could be an important material class to look at for the function that we have in mind. And then within this defined space, the AI finds an optimum or something interesting. You can call this innovative, but for example, if you a priori say, let's look into a space of possible oxides, and the true solution would be carbides, the AI will not find it. And I think the change will come when we really go to open-ended systems with reasoning, because by working hypothesis and generating reasoning, they might understand, okay, oxides are not good. We need something with a different electronegativity or whatsoever. And then it might come up by itself with ideas to switch to a different material class. But that is for the future. Up to now, it is, as Nicola has said, so like it helps us, it frees time for us to really work on the truly innovative kind of things and takes care of daily stuff.
Thank you. We have several other questions. I will just take one for a very quick answer about training because of young people. The question is about how do you envisage these materials, these advanced material design and synthesis tools to be taught to the new generation of students, and by whom? I make the question quick. I think it's an important point, but who wants to answer quickly?
Typically,
No one.
it's the
So,
Let me
young.
tell you quickly, the reality. So I mean, obviously, we need to change the degrees that we're teaching completely.
Yeah.
That is a
Yeah.
no-brainer. But trust me, in my daily life, it's not about training young people. It's actually the young kids train me. They push me all the time in front of me because I'm a dinosaur, and the PhD students they grab it all by themselves. They are so eager. They soak this up, and I really have a hard time keeping up. So it's the other way around. It's our generation that should not be lost.
That's a great answer, Carsten. I think that's the wonderful conclusion. I think we are 1 minute. We have 1 minute to go. I will just end by thanking all the presenters, of course, Nicolas, Carsten, Anke, Dimitra, and Geoffroy. I think it was a very lively seminar, a webinar. Thank you, and thank you all to all the attendees.
Thank
You
you,
can
Patrick.
continue reaching to the people. We will try to answer you by written answers for the question that were not answered. And just to end at 3, I will make a very big thank to Louise for organizing all that. That's been perfect. Thank you to all the contributors, but Louise, you have been perfect in organizing all that. It was a pleasure. Keep in touch. Don't hesitate to join us for any other question or comment. Thank you all.
Bye.
Thank
Bye.
you. Bye bye.
Yeah, everyone.